Okay, so today we're going to talk about distributed computing with Spark. And to put this in context, right, you spent a lot of time thinking about how to optimize the performance, parallel performance of single cores, so single chips composed of multiple cores with SIMD units using ISPC and thread-based programming. You thought about how to write data parallel programs with hundreds of thousands of threads using CUDA. We've also talked about how you can use data parallel programming ideas to generate the large number of threads you need to take advantage of a GPU. And today we want to think about how you use data parallel programming ideas to program a distributed computer, right? So a computer composed of multiple separate operating system instances. And the main programming model we're going to be talking about is one called Spark. And I wish there was a podium up here. I could raise this to be higher. But anyway, I'll fix that in future lectures. And so the way to think about this is sort of, how are we going to program hundreds of thousands of cores, right? And so the question then is sort of, something might fail, and you want to make sure that you don't lose data, especially if you think about the main use of distributed computing in this context is data processing, right? And so you want to make sure you don't lose data. So we're going to revisit this whole idea of data parallel or functional data parallel primitives as the way in which we program these distributed computers. And right, so the question then is, given the data parallel programming model, we want to think about how do we make it scale to hundreds of thousands of cores and do that efficiently, right? And then how do we make sure that we can handle faults or cases where parts of the system fails and we can recover from that in a elegant way. And lastly, we want to make sure that we efficiently use memory because, of course, that is going to be the key component that determines the performance that we get. So, the main motivation then is sort of, why would you want to use a cluster of machines as opposed to a single machine, right? And so the key thing, of course, is if you want to process huge amounts of data, hundreds of terabytes of data. For instance, if you're looking at processing the log data from a large website like Facebook, right? So you could do it with a single node, and your performance would be limited by the I/O rate that you could get, the bandwidth to the disk. And if you did it with a single node, it would take you 23 days at the rate of sort of 50 megabytes per second. But if you had 1,000 nodes, then of course you have 1,000-fold speed up in the bandwidth from your storage system. And so that goes down to 33 minutes, right? So this is the motivation. If you want to process hundreds of terabytes of data, then you need to do it across multiple machines because you need the I/O bandwidth to solve the problem. So it's just something we haven't really talked about up to this point. We've talked about compute, we've talked about memory, but we haven't really talked about I/O. And so one of the really big reasons to use a cluster is to get I/O bandwidth, right? But the problem now is that you need to figure out how to program these hundreds of thousands of cores, right? And so you need to think about how to deal with the fact that things break, right? So even if the mean time to failure of a single server is 25 years, you put 1,000 of them together and then something breaks every hour, right? And so you want to make sure that you can recover from that, and you need it to be efficient, you need it to be reliable, and you need it to be a usable framework, a framework that, programmers can, after taking a course like this, can think about how to use. Okay, so the whole idea of clusters is actually being elevated to what is called warehouse-sized computers or warehouse-sized clusters. And so these are the computing infrastructure behind large websites like Google, Facebook, Amazon, and of course there are huge data warehouses with racks and racks of computers networked together in a way that gives you a single computing environment. And the pioneer of this idea was a guy named Luis Barroso, and he came up with this idea of sort of thinking about the whole computer as a the whole warehouse, which is composed of hundreds of thousands of computers, as a single computer that can be optimized together. So you think about the networking, you think about the power and the cooling, and the programming model. And I mentioned Luis because he's a great computer architect. He recently passed away, and he was a good friend of mine. So, this is somebody, if you want to kind of go look at his book, it's called, Data Center as a Computer. It's a great book, a great primer on sort of how to design systems like this. Okay, so warehouse scale computers, what are they all about? Well, they came out of this idea of a cluster, right? So you take a commodity PC and you connect them together with Ethernet. Right? And so the idea is now you've got this scalable computer, right? And it's fairly cheap because it's based on these commodity PC components, right? Which, everybody in the world, especially when this idea was kind of first invented in the early 2000s, had a PC on their desk. And the idea is, okay, well, if we network them all together, we can get this large scalable computer, right? And so the Ethernet networks of those times were not that fast. Today we're in the 10 to 40 gigabits regime. And the notion is that now you could build this large-scale computer, and you could build it out of these cheap components, and so the whole thing was relatively cheap compared to the big computers that were used in scientific computing. High-performance computers, right? But it turns out that as people started to think about programming these computers and using these computers in places like Google and Yahoo and Facebook, they found out that really the big thing that differentiated the clusters from the supercomputers was the network. And that having a really powerful, high bandwidth network could dramatically make the development of applications easier. And so it turns out that they actually kind of took a page from the supercomputer systems when they were building these warehouse scale computers, and they decided to use a customized, expensive network. And so now, of course, the cost of these warehouse scale computers are kind of edging up into the realm of high performance computing supercomputers. Right? So the question then is sort of, given this style of computer, how do you organize computations on this architecture and mask this issue of, how do you balance the load across 100,000 CPUs, and then how do you mask failures? Right? So the first thing we need to understand in order to figure out how to do this is sort of how these kinds of systems are organized, right? So the way to think about it, as I said, you've got, hundreds of racks of computers, and each of the racks is organized in the following way. At the top of the rack, you've got this top of rack switch, which is the networking interface to the rest of the racks in the system. And then within the rack, you've got, a stack of computer servers, and you can have 20 to 40 servers, and how many servers you can fit in the rack is really dependent on the amount of power that you can actually deliver to the rack. And that will be dependent on what infrastructure you've built in the data center, right? So that could range from 12 to 20 kilowatts, right? And if these racks, today, if you're in the ML regime and they have GPUs in them, then of course the number of computers you can fit in the rack is dramatically lower, right? Because GPUs take a lot more power. Right, so then the way to think about it then is, okay, so within the rack, you've got the nodes or servers are connected between 1 to 2 gigabytes of bandwidth, right? And then, between the racks, right, so outside the racks, early on it was maybe 1/10 of a gigabyte. Today it might go up to 2 gigabytes. So let's look at, what an individual node looks like, right? So you've seen this picture before, in the sense that you've got maybe a 2-socket system, which means 2 CPU chips. Each of those chips could contain 16 to 32 CPU cores. And then they're connected to DDR chips, which provide the main memory. And you might have 128 to 2 terabytes of DRAM main memory. And the bandwidth channel between there is roughly 100 to 200 gigabytes per second. And then from the I/O point of view, then you've got I/O, which is to storage, which is solid state disk, which would give you 10 to 30 terabytes of storage. And then the other I/O interface is to the network, right? And so you can imagine then racking and stacking these servers to create these racks of computation. So any questions at this point? Yeah.
So I didn't understand what's the difference between node and a server.
The same. I use them interchangeably. Okay? You think about a node as a computer which is running an operating system, right? So all of these nodes are running a separate operating system. Okay, so it's important to understand that. So one thing that I should point out then is kind of you take a look at this picture. So, what are the new system components that we've mentioned that we haven't really introduced before? Yeah? Network and?
Solid state.
And solid state storage, right? So these two I/O components, right? So what's the other thing you notice about when you kind of look at the bandwidths that are shown in this diagram? What conclusions do you make about the bandwidths that we see in this picture? Yeah.
The main bottleneck is networks. It's even slower, potentially, than writing to hard disk.
Right. So what you see is that the network, especially in the early days when you've got 0.1 gigabytes of bandwidth between the racks, this is maybe a tenth of the bandwidth you get from going to your local disk. Okay? So that's one thing to point out, that the network is potentially has lower bandwidth than accessing your local disk. What's the other point to make?
Oh, I was going to ask, why is there a difference between the bandwidth for the network and the nodes in other racks? Like, isn't the communication between nodes and different racks through the network?
Yes, but what you have is you've got within the rack you have a higher bandwidth network than you have between the racks, right?
Yeah.
At least to a first order, okay? But then we're going to make another point in just a moment, okay? So what other point? Before we talk about the network, what other things do you see here when you're looking at the bandwidths? What's the relationship between the memory bandwidth and the network and disk bandwidth? Yeah. In fact, your 2 orders of magnitude, right? That's a big difference, right? All right, so that's the one point. But the point about networks, so I made this point about the fact that, in the early days it was kind of commodity Ethernet, and then the warehouse scale computers guys really got serious about their networking capability, and they started making the network much higher bandwidth, right? And so if you're in the 2 gigabytes per second, then that's roughly the bandwidth that you're getting from the solid state disk, right? And so at this point, right? So at this point, it may be the same bandwidth to get data from another node's disks as it is from your local node's disk, right? So in the early days, that was certainly not the case, right? When you're down at 0.1. But when you get up to 2 gigabytes per second, now the picture's changing, right? Right? Because now you can get potentially the same bandwidth to a remote node's disk as to your local disk, okay? So, good point, something to keep in mind. All right. Okay, so I said that all of these nodes are running different operating systems, okay? So what does that mean about how they can communicate? Can they share memory? They can't share memory, right? They're not touching the same address spaces at all, right? And so what we need to do is we need another mechanism for communication, and that mechanism is called message passing, okay? Which is like kind of sending a letter or sending a note to your friend. Okay, and so the abstraction is I'm a thread in some address space, and I've got some variable x that's in my address space, and I want it to send it to another thread that doesn't share my address space, and so I issue a send call, and that I give it the address of my variable x in my address space. I say which thread I want to send it to, and I might give it some message ID tag. Okay, and that will be the send, and that will go over the network and land at the thread. Of course, you can do message passing on the same node, but if you've got separate address spaces. But let's assume that it's going over the network, and then on the thread running on a different node, thread 2 does a receive, and it receives the message and puts it in its variable in its local address space y. Okay. So it receives the message, right? And so this communication then happens with sends and receives. And the question is, if you've got message passing, do you need synchronization? See somebody shaking their head yes, somebody shaking their head no. So what's the answer? So someone who says yes, why do you think you need synchronization?
Because if you're receiving a message, right, then you need to wait for the other person to send the message before you can carry on. Because if you don't do that, then things can go awry.
You could potentially deadlock if you're waiting for a message that is never going to arrive. But do you need explicit synchronization? You would say no.
Not really.
No, because the act of sending a message is the synchronization, right? Okay, so you don't need explicit. You can get deadlock. So that was the issue you were thinking about. That's true. You could deadlock, but you don't need explicit synchronization. Okay, so we've got send and receive. So we have a mechanism, an abstraction for communicating between these separate address spaces that could potentially live on the same machine, but in this large distributed system are typically going to be on different nodes. Okay, so first order of business, right? We're going to use this distributed computer system for doing data processing, right? And so the data's got to live somewhere, and it's going to live somewhere in the storage system. But we said you've got potentially hundreds of thousands of components, and the components could break. Right? And you could lose a node, or you could lose a whole rack because the networking at the top of rack, breaks. And now the question is, how do we ensure that we don't lose any data? We're using this this computer for data processing, and if we lose data, then it's kind of failed in its first goal, right? So how can we store the data persistently? So the answer is, well, let's build a distributed file system. So, any of you been introduced to the idea of a distributed file system? Okay, yes, some of you. All right, so we'll just talk briefly about it here. So, the idea of a distributed file system is that you've got some global file namespace, and kind of the idea was pioneered by Google with the Google file system GFS. The open source version was Hadoop. Distributed file system, HDFS, right? And so, it was predicated on a particular usage model, right? And the model is that you've got large files, potentially, tens or hundreds of terabytes, and that the data that you write to, the kind of access pattern that you use with these files is that you basically just append data to the files in terms of writes, and then you read. So it's mostly read and append, and very rarely do you update the data in place, because a big use of this is for storage of log data, right? So log data, you just essentially, as the new entry for the log gets generated, it gets appended to the log file, right? Okay, so reads and appends as the dominant access mode for this distributed file system. Okay, so the idea then of a distributed file system is to, divide your huge file up into chunks or blocks, and these are usually 64 to 256 megabytes in size. And then, in order to make sure that you don't lose data, you replicate the chunks. And where would what kind of replication scheme would you want to come up with? Here. Would you put all of them all of the replicates in the same rack? Probably not, right? So you want to distribute across multiple racks, so that if you lost a top of rack switch, you wouldn't lose the data. So then the idea then is you've got a master node. The master node is going to basically it's got the metadata, the directory for all of the where all the replicas are stored, right? And so the idea then is you've got a global namespace, right, across the whole distributed file system, and the way that the clients access files is they talk to the master, they find out where the replicas are, and then they go read directly from the replicas. So this is kind of shown in this this figure here, right? So you've got a name node or the master node, and that has the metadata, and you've got a client that wants to read. So first of all, it goes to the name node, finds out where the replicas are. That's step one, and then in step two, it goes to the particular data nodes, which actually have the data, and it picks up the block from one of the replicas. And then if it's, that's client number one, client number two wants to do a write, and so of course it has to update all the replicas, right? Because it got that information about where the replicas exist from the name node. Question?
You still need to kind of, or at least in like a single computer file system, you kind of buffer the writes and make sure that, hey, I don't have the same guy writing the same thing. I have some determinism that I don't accept I have to see.
How do you make sure that the multiple clients aren't...
You need to do synchronization across all the racks.
Well, typically you make sure that sort of only one of the clients is writing to, you handle that at the application level, right? Yeah.
Do you have like a global master node for each drug and for each node?
No, there's a single master node that may be replicated, right? Turns out that, if you've only got a single node, the chances of failure are not that high. The issue is, of course, if you've got thousands of nodes, yeah. But of course, you may want some duplication, maybe to handle the load, right? And sort of you can imagine that in a system with enough high enough usage, right, that you might need to duplicate to make sure that you can handle the load, and you might want some duplication to make sure that if a node fails, you still have a backup. Yeah.
Since we are replicating 2 to 3 times, so does that really mean like in my entire cluster I'm just using 50% of my memory?
Yeah. Or storage. Yeah.
This looks very similar to the file address table FAT storage method. You have like address table for where all your files are, and then you go look at it. Is it very similar, or are there other?
To what?
FAT, like files, file address table.
Storage.
Yeah, it's similar. Yeah, but it's distributed. Yeah. Okay, so now we have a way of persistently storing data such that we never lose data if one of our components in our distributed system fails. Okay? So now, here's the problem we're trying to solve. Suppose CS149 gets even more popular than it is today. Everybody who majors in CS and everybody outside wants to understand and learn about parallel computing, and so the website is getting tons of page views, right? So here's a log of page views from the course website, and your goal is to understand something about these page views, right? So you imagine, right, that we're going to store these page views on a cluster of 4 nodes. It's our tiny cluster here, but we'll give you an idea, right? And so each of the nodes has a 10 terabyte SSD, and you've got some number of blocks associated with each of the nodes in the system, right? So you've divided the large log file into 256 megabyte chunks that we're going to call blocks, and then we're going to distribute the blocks across all the nodes in our cluster, in this case 4 nodes. Okay, so we've got we divided the file into 4 blocks, into 8 blocks, and distributed it across the 4 nodes. Okay? All right, so what we want to know is, who's accessing the site, rather than who's accessing, what type of device are they using to access the site? So what type of mobile phone are the students using? Because, of course, who accesses websites using anything else these days, right? Okay, so you could potentially write a program to analyze the log file using message passing, right? So we're not going to talk about it in this class, but you can program these distributed computers using message passing, using send and receive and what's called collective operations. There's a API called the Message Passing Interface, MPI. I encourage you to go look at it if you're interested. But believe me, it would be painful. And furthermore, it wouldn't necessarily handle fault tolerance, right? So there's one thing, we've got this persistent distributed file system which makes sure that you don't lose any data once you put data in the file system. But what happens if in the middle of your computation you lose one of the nodes, right? And the data that you have is in memory, right? Then you've lost that. So MPI doesn't help you there, right? So you need some other way of dealing with fault tolerance beyond just having a file system that doesn't lose data. All right, so MPI is an option, but it's not a very good one, and it's not easily programmable. So let's think about how you might want to, or how you might want to think about programming the application. So let's go back to the idea of data parallel operations, right? In particular, map and reduce, right? So just to refresh your memory, right? So the map is going to take a collection or a sequence, in this case of type A, and create or produce a sequence or collection of type B. And the way that it's going to do that is going to take each element of the input sequence and convert it to an element of the output sequence, right? So what do we set? There are 2 things we said about map that we could do, that are important. What's important about map? Yeah?
It's easily parallelizable.
It's easily parallelizable, right? So because, of course, we know there are no dependencies between the different elements, right? So we can do the elements, we can create the output sequence in any order. What's the other important thing about map?
Something fails.
Why is that?
Well, like side effect free unity function. So
Side effect free. So what does that mean?
which means you can run it again and again and again on the same input, same output.
And why is that?
Because it's bad, we can access that piece of things that input in memory and write it to that output.
Because map does not mutate its input, right? Doesn't change its input. So the input never changes, so you can run it as often as you like and generate the output, right? Good. So that's an important point to remember, that sort of these data parallel functional operations, the key thing about functional programming models is they don't mutate their input, okay? And because they don't mutate their input, it has all these nice properties of side effect freeness, and which will have, I think you're alluding to the fact that has some fault tolerant benefits that we'll definitely talk about. All right, so the other operation is reduce, right? So reduce will take a sequence of type A and produce a single element of type B by using some sort of reduction function. All right, so now let's think about the map-reduce programming model and a way of counting the page views of a different type of each type, right? So the key elements of the map-reduce programming model, of course, are a mapper function, which is shown here. Oops. And a reducer function, which is shown here, right? So the mapper function is called once per line of the log file, and it parses the line and figures out whether the line is from the entry is from a mobile client. Okay, so it figures out whether it's from a mobile client, and if it is, it records a entry or updates an entry in the result map, right? So the input to mapper is a single line from the log file, and the output is a map of results, right? And so it's going to add an entry to the map data structure, and then the reducer function is going to be called for unique keys, all the values associated with the unique key, and it's going to be called once for each unique key. And what it's going to do is it's going to take the string of values and just add them up, right, to create a sum, right, which is the result. Okay, so the idea then is we generate these key value pairs in the mapper function, and then we reduce these key value pairs in the reducer function, right? And so the code at the bottom shows how things get called. First of all, we get the input from our distributed file system, and then write the output again back to the distributed file system. And that happens when we run MapReduce job with the mapper function, the reducer function, and the input and output. Yeah?
Is that map and reduce here mutating its inputs because it's adding to the map and setting the result?
So the way to think about this is that the input to the map is really the data that you get from the distributed file system, right? So you can think about in this case, you can think about the kind of results as sort of internal to MapReduce, right? And so the interface is really, the API really has to do with the data that you give to the run MapReduce job, right? And so, the input doesn't get mutated. Okay, so let's think about actually implementing run MapReduce job. And so the way to think about things like, is, so I'm going to show you the kind of classic, MapReduce 101, which is word count, right? All right, so the idea is that you have one map task per block of the input file, right? And so in this case, we've got 3 blocks, and so we've got 3 map tasks. right? And the map task, read lines from the input blocks, and they create this set of key value pairs. And so here we want to count the number of word occurrences in the input file. And it creates an entry, a key value pair, which has a 1 associated with all of the words that it found in the input files, right? And so you've got 3 sets of, or 3 maps, three instances of key value pairs associated with each of the mapper tasks, right? Okay, so now, in this case, we've got 2 reduced tasks, right? And so the question, so in the mapper tasks, the parallelism is obvious, right? It's associated with each of the input blocks. How about the reducer tasks? Where do we get the parallelism from for the reducer tasks?
Separately.
Right. So you're going to associate some number of keys to each of the reducer tasks, right? And so that's where the parallelism is going to come from. But what happens when you do that? Yeah.
How do we know the reduced task is associated with? Like, if we start given some random reduce function, how do we know that we can actually split it up and get the same thing?
So it won't work unless you have an associative reducer. Yeah, that's right. So that's kind of part of the limitation of MapReduce. If you want to parallelize it, at least, yeah. So, but for what happens once you do this? So who said we want to get the parallelism by having multiple keys being operated at the same time by different reduced tasks? So what do we have to do in order to make that happen? Yeah, somebody said something.
Synchronization.
Synchronization of what sort? Somebody back there. What's the answer to sort of what if we've got to parallelize across keys? What do we have to make sure happens in order for the reduction to be correct? Yeah.
All keys go to the same.
All the keys of the same type or the same value have to go to the same reducer task, right? And so the way to think about this is map reduce is really map group by key reduce, right? Or there's this big sort or shuffle in the middle to make sure all the keys with the same value go to the same reduced task, right? And so that's the way to think about MapReduce. It's really map group by key reduce, or some people say sort or shuffle, right? In the middle, in which you've got a lot of communication that is potentially going to happen between the mapper tasks and the reducer tasks, right? And then we're going to talk more specifically about sort of how you make sure the keys of the same value go to the same reduced task. Okay, so let's run the mapper function. So here's our MapReduce code, and we want to run the MapReduce job, right? And so the first question is, we've got these mapper tasks associated with each block. How should we run them? Anybody have ideas about how we should run them? Yeah.
Can we run the same node as in block?
That's one idea. We could run the same. How do we make sure things get load balanced? What if we're really concerned about load balance? What would we do? Yeah.
You could do something like the thread pool, right? Like make one node like a master node and have like all the tasks queued up there, and have the other ones keep sending messages to get in the next task.
Right. Use a work queue or some sort of distributed work queue to make sure that we had extreme load balance, and this might work well in the case where we had a really powerful network, right? That second case I talked about having bandwidth in the network equal to what you might get to your local hard disk. But what if, in the early days of MapReduce, when the network had much less bandwidth than the bandwidth you get to your local disk? Then we had another idea, which was proposed first, which was what?
Run it on the same.
Yeah, run the task associated with the block on the CPU that actually contains, on the node that actually contains the block, right? So this idea is sort of data distribution or task distribution. Each processor node processes lines or blocks in the input file that are stored locally. Okay. All right. So now we've got all the mapper tasks, and we've created all these key value pairs associated with the different mobile clients. And now we have to do the reductions, right? So we got all these keys, which have been generated by the mapper function. Okay, and so now we have to make sure that we can do the reduction. So there's two questions, right? How do we assign the reducer tasks, right? And then how do we make sure we get all the data for a key value to the correct worker node? So who has ideas about what we should do to assign the reducer tasks to nodes to run? Yeah.
Use a hash function and then group by the hash value.
I think that's answering the second question. What about the first question? About where the tasks are going to run? Yeah.
See what threads are spinning with no work to be done and are available, or I guess CPUs in this case, and assign it to them.
Right. So you some sort of scheduler which is looking at you have some set of nodes which are going to be reducer nodes, right? And you have a scheduler which is going to assign tasks, right? But the question then still is sort of who is actually going to, how are you going to make sure that the data gets to the right node? Right, and so somebody you had an idea for that, right? Which was use some hash function, right? Based on the key value. And then use that as the partitioner or you use that as the information given to the mapping task nodes, and that will indicate where those nodes should send the key value data to be reduced, depending on the key. So example is assign Safari iOS to node 0, and then we know where to send the data to, and where the task is going to run, where the reducer task is going to run. Okay? So in different systems that work different, some ways kind of decide up front, and so the mapper, declares what key value pairs it has, but it knows where to send them ahead of time. And others might decide, once all of the mapper tasks are complete, right? Because you can't do any reduction, right, until all the mapper tasks are complete. So there has to be a barrier between the mapper tasks and the reducer tasks. Yeah.
Would this system be aware of the, so in this case, Safari values are all equally distributed among the 4 nodes, but say like 3 of the Safari values were a node 1, and 1 of them was a node 2. It would be more efficient to get it.
Yes, you could imagine a locality-aware scheduling mechanism that took that into account. Good point. Yeah. All right, so we have a mechanism for deciding. You could use the scheme that was just suggested, where we try and group the reducer task. We put the reducer task on the place where most of the key value pairs already exist in order to minimize data movement. Or we could, in the instance of, hey, I've got a really powerful network, it may not matter, right? All right, so we've solved the, key problem of executing the mapper and reducer function, using these different tasks associated with either different blocks of the input file or different keys. But what if I've got, thousands of nodes? There are a couple of issues that could crop up. One is that, some of the nodes may fail, as we've talked about, right, during the computation, right? So we're not going to lose any data, right, because we have made sure that, that we've got a file system that is fault tolerant, but we need some way of making sure that we can recover the computation and make sure that the computation will complete successfully. So that's one issue. The other issue is that if I've got a huge data center, I'm not going to have all the nodes in the data center be of the same vintage, right? You may refresh the data center over time, over the period of maybe 3 to 5 years. And so I'm going to have some older nodes, maybe with fewer cores and maybe a lower clock rate, and some newer nodes with more cores and maybe a higher clock rate. And so some of those nodes may finish faster than other nodes. And so how do I make sure that I can deal with this problem? And so the key thing then is to have a job scheduler that handles these issues, right? So it exploits data locality, runs mapper jobs close to input blocks, runs reducer blocks as reducer jobs or tasks as was suggested, close to the place where you've got most of the data. And in particular, it handles node failures, right? So basically, you've got a heartbeat, which is each of the nodes regularly sends a message saying, "Hey, I'm alive," to the master node. The node is doing the job scheduling. At some point, if that heartbeat goes away, then the node is declared to be dead, and the scheduler has to figure out what to do. Okay, so what can you do? Well, once you detect a failure of a mapper node, what should you do? Yeah.
You go to another one of the computers that has the copies of the storage and then run.
Right. So you go somewhere else, right, and you fire up the tasks that were running on that mapper node, and the data will come from blocks that have been replicated in the system, right? And the fact that you've got this functional data parallel model in which the inputs are not mutated guarantees that that's a safe thing to do. And so now you're going to create a new set of key value pairs that can be reduced. So what happens if a reducer fails? Yeah.
We need to send all that data to a new producer.
What if it fails after it's done? Does it matter? If the reduce tasks are complete, then it doesn't matter, right? But if they're in the middle, then you've got to restart them, and the data has to be, either it's got to go get the data again from the file system where the key value pairs were stored. So how do you handle slow machines? Well, the scheduler can just replicate multiple reducer or mapper jobs. If the machine is taking too long, it'll say, I'll just fire off a new job, and then it'll be a race, right? So if the slow computer finishes first, then that result will be taken, and the replicated job will be killed. Otherwise, if the replicated job finishes first, then you can kill the slow machine. So duplicate and handle multiple machines, and this is all possible because of this kind of data parallel functional programming model. Yeah.
Couldn't we have some sort of a metadata or heuristics to avoid wasteful computation? Like in this case, we are killing a node which is not doing any useful work in it. Like if you had metadata that this machine is generally faster, this machine is generally slower, wouldn't you schedule for it?
I suppose you could. but that, then, is extra sort of complication in your scheduler, right? Yeah. And, what happens when the machine, then it's got to, keep track of sort of what machines are of what vintage and so on and so forth, and how loaded they are. That becomes more of a scheduling issue. Yes?
What if the job schedule fails?
What if the job scheduler fails? Then you're out of luck, your whole. Well, I mean, so as I said, you've got a single node. The chance of that failing is not that high, but, you might duplicate it. All right. So the advantage of MapReduce then, of course, is that gives you this nice data parallel programming model. MapReduce, it's fairly easy to understand. I can explain MapReduce to most CS undergrads and they would get it right away. Whereas if I introduce them to message parsing, it would be a difficult process, right? So you got this automatic division of jobs, of the job into tasks, either mapper tasks or reducer tasks. You've got this load balancing that happens because you've got many mapper tasks and many reducer tasks. You've got locality-aware scheduling, and you've got this idea of being able to recover from failures and stragglers. So it's a pretty nice programming model, and it made it possible for mere mortals to program hundreds of thousands of CPUs. For sort of doing these data processing tasks. So it really took off, and it became an idea that actually had widespread use even beyond distributed computing, right? Where we've already seen it in the context of sort of GPU computing, and it's being used in other areas too. However, it does have some issues, right? And the first issue being the programming model is pretty simplistic. The only thing you can do is have a map followed by a reduce, followed by a map, followed by a reduce, and so on. So it's a fairly kind of this linear arrangement of map and reduce functions, which kind of limits what kinds of applications you can write. And so there was a extension to a directed acyclic graph. The work was called Dryad Link, and it certainly had some academic impact, but it didn't get much adoption as far as I can tell. But it's an interesting idea. If you're interested, go and look up the Dryad Link paper. It's a pretty interesting paper. Okay? And how about iterative algorithms? So PageRank, everybody's heard of PageRank, right? You want to understand the importance of a particular website, then you compute PageRank. It was originally invented by Larry Page, right? So, one of the founders of Google. The idea is it's an iterative algorithm, and if you implement it using the MapReduce model, then every iteration requires a distributed file system read followed by a distributed file system write. Okay, and this could go on for many iterations, and so it becomes fairly inefficient to run this algorithm using MapReduce. Another area where MapReduce doesn't work so well is if you've got a set of data and that you want to query in some sort of ad hoc way, and this is, often happens in interactive data processing applications, right? So you've got some data that exists in the file system, and you've got a bunch of ad hoc queries, and each of them requires this access to the file system, which is not very inefficient, right? So even though then this MapReduce has all these nice properties, and as I said, had a huge impact in the ability for programmers to develop these distributed applications, these kind of limitations, led to people thinking about more efficient ways of using the computation. And sorry for the font, the way the fonts look on this slide, but the key point is to remember what we said about the relative bandwidths between the memory versus the network and the storage devices. And so what we want to do is to think about how we can make much more intensive use of the highest bandwidth interface on this picture, which is the memory. So what is the problem? Well, before we talk about the problem, let's talk about kind of further motivation for why we potentially could use the memory more intensively. So this is a table from a paper called Disk Locality in Data Center Computing is Considered Irrelevant, right? And that's from a paper published in 2011, right? So part of the reason that it was considered irrelevant was the point that we've already made, which is the networks were getting much more bandwidth capable, right? But the other reason is shown in this table, which is data from 2009, and it's looking at the working set of the big data applications at Facebook, Microsoft, and Yahoo. And it's showing that with 64 gigabytes of memory, 97% of the working sets of data at Facebook can be contained in the memory, 98% at Microsoft, and 99.5% at Yahoo, right? So the point here is that you really can keep most of your data in the memory. The memory's big enough. But the programming model forces you to shuttle this data back and forth between the storage devices and the memory, right? So the question is, could we come up with a programming model which is just as nice or even better than MapReduce, but allows you to use the memory much more intensively? What would be the problem? Yeah.
Oh, this thing that all the data fits in a single node disk, or like that the data fits in like all the nodes.
All the nodes disk. So for all the nodes that you're running, the data will fit in the local memory, not disk.
Oh, okay.
Yeah.
Yeah. Including the replicas?
The replicas have to do with the file system. It's talking about you're actually doing the computation. You're in the middle of the computation. Will the data fit in your local, in the memory? Or will you have to, make use of the disk? It turns out you can actually do the computation by having by keeping the data in memory. Okay? Yeah.
I guess your computation still depends on memory. Sorry, if the data fits in another node's memory, you still have to communicate between nodes.
Yeah, so this is talk about working set, right? Which is sort of most of the accesses are to data that lives in memory. Okay? There's not all the accesses, right? So you still get to move some of the data from other places. The question is, we talked about locality, right? So you've got reuse, you've got spatial locality, right? So this is just talking about working set, right? Which is a concept that you should have, we should have talked about in an operating systems class, right? There's a notion of sort of what is the set of data that you're actively using, right? And that is what they're trying to measure here, right? Okay, so what would be the problem with using memory instead of the storage system to hold the intermediate data in your computation? Yeah.
If you lose power, you're screwed.
If you lose power, you're screwed, right? You're going to lose your computation, right? So the whole idea of Spark was in-memory, fault-tolerant distributed computing, right? With emphasis on the fault-tolerant piece being once you lose power, you don't want to be screwed. Okay? So the goals were, can you have support for iterative machine learning algorithms, data mining algorithms that in which you will kind of keep your data in memory. So you don't want to incur the inefficiencies of writing the intermediate data to the disk, because we said that's a low bandwidth, low performance data path, and what you want to make sure is intensively use the high performance, high bandwidth data path between the CPU and memory. Okay? So the challenge then, of course, is how do we make sure that we can do this efficiently and we can efficiently implement fault tolerance for this large-scale distributed memory, right? So the solution that we've come up so far is, oh, we know how to do a fault-tolerant storage system, so let's just use that. That's the MapReducer solution. But that's a low-performance solution, right? So what we want is a higher performance solution that, relies on memory. And so that's Spark, right? So, we talked about you could kind of checkpoint and roll back, but then the question is sort of how do you do that, and how do you make sure that you distribute your data to different racks? So it could be network intensive. You can maintain a log of updates, but it could be a high overhead to maintain these logs. So that probably is not going to work so well. And then you could go to a low performance solution like we've talked about in the case of MapReduce. Okay, so in this case, we're going to checkpoint after each MapReduce by writing results to the file system, and then the scheduler is going to make sure that it's keeping a list of sort of what needs to complete, and it will rerun things that fail. And the functional structure of programs allows for the restart at the granularity of the mapper or reduce task. Okay? All right. So, how does Spark solve the problem? So the first thing Spark does is introduce this idea, which is central to the approach, which is the idea of a resilient distributed data set, RDD. So this is Spark's key programming abstraction. And what is an RDD? It's a read-only ordered collection of records. So it's immutable. So this idea of the RDD is it's functional in nature, right? So once you think about functional programming, RDD is a fairly natural construct, right? And so RDDs can only be created by the transformations from other RDDs or from persistent storage. Okay? So, for instance, if I start with our CS149 log, which is a text file which is stored in our distributed file system, right, I can get the lines from that file to create an RDD called lines. Okay? So that was a transformation from the file system to an RDD called lines. Then I can use a filter transformation, right? So I have lines, the lines RDD, and I'm going to apply a filter transformation to see whether this is a mobile client, and then the what I'm going to get is mobile views, lines that correspond to mobile views. And so this is another RDD, okay? And then I'm going to take the mobile views RDD and I'm going to filter it again to see whether the string contains Safari. And if that is true, I'm going to create it's going to be entered into this new RDD called Safari views, okay? And then finally, I'm going to take Safari views. I'm going to apply a action, which will essentially give us a count. It's kind of a reduction, which of course it's going to create this int, which is not an RDD, right? But the RDDs are lines, mobile views, and Safari views, and the sequence of operations that create the RDDs is called a lineage. And we'll come back and revisit this idea. Okay? So this is the main way that you program using Spark. You start with some data in the file system, and then you apply transformations to that data to create different RDDs to encode the logic of your program, right? And each of the RDDs is, of course, read-only, and it's ordered, and it's immutable, right? And these turn out to be very useful properties when you're trying to build a fault-tolerant system. All right, so we talked about the fact that you can write using Scala, you can write all this in a fairly functional way, and you can create, in this case, you create an RDD from the file system, and you don't have to explicitly call out the RDDs. And the sequence of operation or transformations then, as I said, called lineage. Right, so in this case you do your operations of filter, map, reduce by, and collect. Sorry, reduce by, collect is an action. It's not a transformation. Okay, any questions? So you've got this concept of the RDD, the resilient distributed data set. You've got this concept of a lineage. So how can we kind of optimize things with Spark? Well, we have this notion of persist, which says keep the RDD in memory, right? And so in this case, we create our mobile views RDD, and then we're going to use it twice. Once we're going to filter for Chrome, and then collect, take the lines, the strings that are in the RDD created from the filter, and extract timestamps, I should say. And in the other case, we're going to filter based on Safari and figure out the number of views, page views that came from a Safari client. So here are the set of transformations that you can use in Spark, right? So you've got map, filter, flat map, sample, reduce by key, join, sort, partition by, which we're going to talk about in just a moment. And then you've got actions, right, which of course create data back to the host, like count, collect, reduce, lookup, save. All right, so with these operations, you can write very sophisticated applications. So let's think about now, any questions on sort of the programming model and abstraction that Spark presents, right? So it's the notion of the RDD and then these transformations and actions. Yeah?
By default, every transformation consumes the previous RDD, like it will finish the RDD. Like why do we need a explicit persist?
So persist just says keep the RDD in memory.
It will be deallocated, right?
Well, it may not keep it in memory, right? So it's not going to I mean, the RDD will exist potentially in the file system, right? The question is, will it stay in memory, right? And that's what persist says. Keep the RDD in memory.
How do we decide which RDDs get persisted in the file system?
Well, you can say explicitly, right? The scheduler can make some decisions, or you can say explicitly, right? Yeah.
One question is, like, if you don't say persist and you ask for it again, isn't that recompute it? Or is it going to like stay on storage and then leak?
Yeah, it'll probably save it to storage and reload it, yeah. So it will be inefficient, right? So in the case of the example that we showed here, if you didn't persist mobile views, right, then mobile views would get written to the file system, and you'd have to go fetch it again in order to do, let's suppose you did the left-hand side first, then to do the right-hand side, you'd have to fetch it again. Yeah?
One more question is, like, when you're hitting the collect, it's kind of clear that you've run it in both cases. If you have like a that can spread out count as something like if you make numbers and timestamps like some sort of lazy variable, not Spark do the optimization for you.
Do what optimization?
Like if you know if Spark knew that mobile views is used by two operations, then can it not just like leave it in memory, do it both, and like kind of do that optimization?
Yeah, could. Yeah. Sometimes you've got to help the system, but other times the system, can analyze. And as I'll describe, the Spark run system does a bunch of analysis, and we'll do optimizations for you. And we'll talk about one in just a moment. Okay, so let's think about how we can implement RDDs, right? So imagine that here are the RDDs we've got: lines, lower, mobile views, and how many is not an RDD, but lines, lower, and mobile views, right? So if you think about the fact that this is going to be these are going to be partitioned across the nodes, right? So let's assume that there are two partitions on every node, right? So lines partition is used to create the lower partition, which is used to create the mobile views partition, right? So one way would be we could think of these as arrays, right, that get duplicated in memory, right? But that would lead to a lot of memory use, right? Right. And so the question is, how can we implement this data parallel RDD abstraction in an efficient way such that we minimize the use of memory, but we still keep all of the fault-tolerant capabilities that we want? Yeah.
We don't keep the partitions that we're done with. Like if we're computing lower, or we finish computing lower, we don't need to then also keep the data from lines because we already have the RDD that comes after that, and so we're already
Yeah. That would be a good first step, right? But we might maybe be able to do even better than that. Yeah.
Instead of duplicating the array each time you're doing a filter or any sort of function, you can kind of just have one general array and change the references to the elements in it each time you do a filter. So that way you don't have to duplicate the array each time.
In which case, I mean, so in terms of efficiency, you probably don't want references going all over the place, right? I mean, you want things to be concatenated, and you want things to be dense, right? So having references is probably not a very efficient way of doing things. Yeah. Other questions? Where are we? Oh, running out of time. All right, so let's figure out how we can do things efficiently. So one of the things we could do is think about the dependencies, right? And the dependencies go from the data in the file system through the different partitions of the different RDDs, right? From lines to lower to mobile views. Okay? So the question is, thinking about the fact that we've got these dependencies, can we optimize the implementation of RDDs? And the way to think about it is think back to some of the optimizations that we've talked about so far. So we've talked about the fact that this program is better than that program, right? And why is that?
Less writes to memory.
Right. That's the reason writes to memory. We've done fusion of these loops, and we have reduced the writes to memory, and so improved the arithmetic intensity. Okay? And so we also talked about this optimization, where we use tiling to optimize the use of memory such that we reduce the amount of memory we need to support the blurring, right? And so these two ideas of fusion and tiling are pretty important, and they can be implemented in the Spark runtime system. Okay? So the question is, when can you apply these transformations? Well, if you try and do these transformations on arbitrary C programs, they're difficult to do, right? Usually you as the programmer have to implement them. However, if you start from a high-level representation like Spark or PyTorch or something that gives you more semantic information about what is actually going on, then you can do some of these transformations automatically, right? So fusion with RDDs is possible. And however, you need to know what the dependencies are between the different RDDs. So we have this notion of narrow dependencies where one RDD only depends on one other partition, right? So these are called narrow dependencies, right? So partition 0 of mobile views is dependent on partition 0 of lower, which is dependent on partition 0 of lines, which is dependent on block 0. So these are narrow dependencies in that an RDD only depends on one other partition of an RDD. Wide dependencies are a case where you've got an RDD which depends on multiple RDDs, right? So in this case, if I do a group by key, right, I may have to get elements of the partition from multiple places. And so if I have narrow partitions, then potentially I can have the system automatically do the fusion. At this point, we'll run out of time, so what we'll do is after probably next Tuesday, I will finish up this discussion of Spark and move on to cache coherency. And on Thursday, Kayvon will be back to talk about efficient implementation of DNNs, right?
No, this Thursday.
This Thursday, yeah, right. And then on Tuesday, I'll come back and we'll wrap up Spark and we'll start talking about cache coherency. So sorry for going over time, but it's really interesting stuff.